Thanks for tuning in. My name is Guy, and I will present our work on stochastic coordination in heterogeneous load balancing systems. This is a joint work with Shai Vargaftik from VMware Research and my advisor, Yoram Moses. Let's start with some background. Cloud applications typically employ many servers to serve a large number of clients. Client requests need to be dispatched to the servers in a manner that will ensure efficient and smooth operation. In the standard parallel server model, a single dispatcher directs incoming requests to the servers. Each server receives jobs through its queue and handles them locally. A central goal of the dispatcher is to ensure that no server is overloaded or underutilized. Nowadays, however, cloud services and data centers have grown so large that a single dispatcher can't handle the incoming traffic. Therefore, load balancing through multiple dispatchers is becoming the new standard. Moreover, systems today employ a variety of machines, which include multiple generations of CPUs and GPUs, as well as specialized and accelerated hardware. The result is a very heterogeneous system with a variety of processing rates at the servers. In addition to the challenges stemming from heterogeneity, the high rate of arriving requests does not allow for inter-dispatcher communication, as that would severely damage the client experience due to the extensive buffering while dispatchers deliberate on what to do. Let's talk about existing solutions. The most straightforward and simplest approaches to implement are the uniformly random or the round-robin dispatching. But these approaches do not take into account the actual server loads, and therefore lead to imbalanced allocation and degraded performance, especially at high loads. There is a significant body of work on load balancing with a single dispatcher. For example, join the shortest queue, which, as the name suggests, sends each job to the server with the shortest known queue. Join the least workload and shortest expected delay also take into account the load at each server, making them suitable for systems with heterogeneous servers. However, these algorithms all suffer from a significant problem when they are used in a setting with multiple dispatchers. In all cases, when a dispatcher detects a good server, it forwards its job to that server. A problem arises when multiple dispatchers detect the same good server. A good server. They all simultaneously forward their jobs to this single server, causing its queue to explode. This is known as the herding behavior. This problem is severe enough to also be dubbed the finger of death. Some load balancing algorithms are designed under communication constraints, or partial visibility. In power of choice, for example, the dispatcher samples only 2 servers and sends jobs to the server with the shorter queue. These algorithms reduce herding, since different dispatchers have different views of the server states, and so dispatchers are unlikely to target the same server. But this comes at a cost of suboptimal performance, especially when the information is available, as is often the case in modern systems. The paradox of these limited visibility algorithms was noticed in our work from last year. That is, how better information leads to degraded results. And those mentioned algorithms only perform well when they are in a particular sweet spot of available information. If they don't have enough information, they are reduced to random. And if they have too much information, they lead to herding. The former work suggested a remedy to the information paradox to explicitly address the coordination among dispatchers problem through carefully inserted randomness. Each dispatcher considers the current system state, the current load at the servers, and computes a probability vector that assigns higher probabilities to less loaded servers. Crucially, the calculated probabilities must also take into account what other dispatchers might draw, considering that they see the same system state. A dispatcher then independently draws the destinations for its jobs according to its probability vector. We are left only with finding these probabilities. Finding the optimal probabilities means solving the stochastic optimization problem. In the homogeneous case, the problem admits an efficiently computable closed-form solution, as we showed last year in DISC. However, the problem cannot be solved in the same manner in the heterogeneous case. To illustrate the problem, the optimization problem, is consider the highlighted dispatcher. Two jobs have arrived to it, and it needs to dispatch them. It knows the state of the servers and must consider what is likely for the other dispatchers to do, given that they see the same system state. Now, our dispatcher needs to compute with what probability to send each job to each server. Clearly, our goal is to find the optimal probabilities. To formalize this stochastic optimization problem, we first define what is an ideal assignment. This assignment balances the load as much as possible given arrivals and the current state. Since servers have different abilities, we define the workload at the server to be the number of jobs in its queue divided by its processing rate. In this example, an ideal job assignment of the 7 arrivals is written in the yellow labels. The assignment is idealized in a sense that it is not always feasible. As we see here, it might require breaking jobs, which is impossible. The ideal assignment defines an ideal workload, 1.375 in our example. Now we can define the goal of the stochastic optimization problem to be bringing the loads as close as possible to the ideal workload. I'm not going to explain much here, just to mention that we seek a probability vector that minimizes the L2 distance from the ideal workloads. This optimization problem has no closed form solution in the heterogeneous case. The way to solve such problems is typically by searching for an optimal solution in the space of all possible solutions. However, in general, solving these problems requires exponential time. Even approximate solutions, such as the interior point method, have cubic complexity, which is unacceptable in existing high-volume load balancing systems. Remember, our load balancing problem needs to be solved with each new round of arrivals, so it must be done very, very fast. The main technical part of our work deals with solving the optimization problem as fast as possible. We do that by both identifying special structural properties of the problem, which narrow down the search domain, and by applying an algorithmic approach to the search. Spoiler alert, we achieve an order of n log n time complexity, which is optimal. In the next few slides, I will give an overview of how we achieve the optimal solution, and then conclude with evaluation results. So, we examine the Karush-Kuhn-Tucker conditions, which are conditions that an optimal solution satisfies. These conditions reveal that in our problem, finding the optimal probabilities can be reduced to finding the servers that have positive probabilities in that solution. We call this set of servers the probable set and denote it by S+. The significance of the probable set is that once it is identified, an optimal solution can be calculated in linear time. But how does it help us? There are exponentially many candidates for the probable set. This is no better than existing solutions. Roughly speaking, we take the following steps. First, we solve the problem with the current state of the servers, but when assuming that there is a single job arrival. Based on that simple case, we give scores to the servers. Using these server scores, we can reduce the set of candidates to n different sets of servers, one of which is guaranteed to be the probable set S+. Finally, we further improve the time complexity by employing dynamic programming. Let's take a closer look at each of these steps. We start by solving the simpler problem with a single arrival. For example, here we have 3 servers with processing rates 1, 4, and 9, which have queues of lengths 0, 1, and 3, respectively. A natural choice is to send the job to the least loaded server. This aims at minimizing the wasted service capacity in the system. In our example, this means sending the job to server 1. Another option is to send the job to the server that is expected to complete it first, namely minimizing the job's expected response time. This means sending the job to server 3. So, what should we choose? Better resource utilization or better response time? Actually, the correct solution is server number 2, since it minimizes the L2 distance from the ideal workloads. This server minimizes the quantity twice the queue length plus 1 divided by the processing rate. Intuitively, this captures the proper trade-off between better resource utilization and shorter response time whenever they are in conflict. In fact, the significance of this quantity goes beyond the solution for a single job. The second step in our solution is establishing a key property of the probable set. We define the score of each server to be the quantity from the previous slide, and we prove that if a server is in the probable set, then every server with a lower score is also in the probable set. The meaning of this result is that if we sort the servers according to their score from small to large, the probable set is one of the n possible prefixes of this sorted sequence. For example, consider the previous example with the 3 servers which score 1, 3/4, and 7/9. Our result means that for any number of arriving jobs, the probable set is either S2, S2 and S3, or S2, S3, and S1. This is the key for reducing the search domain from exponential to linear. Since each candidate set can be examined within an order of n time, we get a quadratic time complexity. Quadratic complexity already offers a great improvement, but it is still slower than existing load balancing algorithms, which often run at n log n time. To further reduce the complexity, we use the fact that the n candidate subsets contain each other. We prove that examining the subsets by increasing order has an optimal structure, and we use that to derive a dynamic programming algorithm that explores all of them combined in an order of n time. Finally, the complexity of the solution is dominated by sorting and is therefore n log n. The algorithm is given in the paper. We implemented the dispatching algorithm in C++ and evaluated its performance in multiple simulations. I'll provide a representative result here for a system with 100 servers and 10 dispatchers, and I encourage you to see the full paper for more results. In this graph, we see the average time a job spends in the system. We measure the mean job response time in round and present it as a function of the demand on the system. The demand is the ratio between the expected number of arrivals and the total processing power of the servers. I'm not going to elaborate on the other algorithms we've compared against. I only want you to see that our stochastically coordinated dispatching algorithm consistently offers the best performance, where the gap widens as the demand increases. This bottom graph shows the interesting metric of tail response times. For example, if we're interested in the 99th delay tail percentile, it means that we're interested in the response time of the slowest 1% of the jobs. This measure is very important for client experience because a client request might be broken into many, many jobs, and the response time the client experiences is the response time of the last job to complete. To summarize, lower is better. Again, it is evident how stochastically coordinated dispatching offers the best performance in this metric as before. Finally, we measure how much time it takes a dispatcher to compute its assignment in each round. Since this time it depends on the particular system state, we show the cumulative distribution function of the computation times. We see that stochastically coordinated dispatching scales similarly to join the shortest queue and shortest expected delay, which all require an order of n log n time. We've shown that our algorithm solves the herding problem and contributes to better overall system performance. These simulations show that our algorithm is also viable from a running time perspective in any system that currently employs JSQ or SED, which is most systems, actually. To conclude, the distributed nature of current day's high-volume load balancing system raises new and interesting challenges. We presented a new algorithm for load balancing in heterogeneous systems with multiple dispatchers. Our simulations show that stochastically coordinated dispatching outperforms the state-of-the-art in these challenging settings. Achieving this strong performance requires solving a stochastic optimization problem. We identified structural properties of the problem that allowed us to reduce the solving time from exponential to polynomial. Additional algorithmic improvements reduce the complexity to an optimal n log n, exactly as join the shortest queue. Now, from a different perspective, this project involves convex optimization theory, algorithmic complexity, and microsecond measurements. Working on such a combination proved to be a lot of fun for all of us, Shai, Yoram, and myself. I would like to thank you for listening until here, and I hope to see you all in person soon.